Hello, Markus Felder here from the Embedder project at embedder.wordpress.com or embedder.com. I wanted to show you a little bit why we have decided to use MPS as a way of explaining some of the benefits of MPS for language engineering. So what we're doing here is we're taking C and extending C with domain-specific concepts to ease embedded programming. So let's take a look what we've done. This is MPS here, and we have built, we've added the whole C language into MPS as another base language. And the goal of the project, as I said, is to extend C with language extensions that are useful for embedded programming. Now, one interesting aspect of MPS is that it supports modular language extension. For example, you can see here a module. Modules contain basically all kinds of things. And by default, a module contains C programs. So I can just go here, put in a main function, and write some C code. Whatever, int x equals 10, return, I should be able to type, return x. And you can see that we are able to extend this. For example, here we have a test case. A test case is a new language concept that we have added to C, but the interesting thing is that it lives in its own language. So if we go to the definition of test case and show it in the project, you can see that there is a unit test language that contains all the testing support for C. You can also see here that we have integrated a new data type. It's basically the data type kilograms, which is internally an int8, and we can use physical units on numbers, on literals. So we've extended C with another modular language with the ability to have physical units on data types. We can do more. We've integrated state machines, right? So this is syntax for state machines with states and, transitions and all the state machine goodness that you typically want. We have extended the statements so we can trigger state machines. We can even verify a state machine, which gives you some information about whether the state machine contains problems. We've integrated the new SMV model checker for doing that. So we transform this to another representation and then run a model checking algorithm that tells us whether the state machine is valid or not. And all this tool integration is easily done with MPS. We have integrated components, right? So this is yet another extension of C where we have interfaces and then components which implement the interfaces. One nice thing about MPS is that it can do syntax that is non-textual. So here you can see a component that contains a decision table. Decision table is basically a nested if statement where you first evaluate the column headers and then the row headers, and you return the value for which column and row headers are true. And the interesting thing is that this language is yet again a separate language which can nonetheless be used within components or within normal C code. I could just write a function here. Some function where I do a return, and I should make this an integer, and then I can put a decision table here, right? And so I can use this anywhere I want. And all of this works because of MPS's projectional editing capability, which makes it very interesting for us. This projectional editing also supports other cool things. For example, here we have a bunch of requirements, which are at this point basically just a hierarchical list of IDs and some describing text. And then we have some code here, and this code contains traces, right? Requirements traces are basically pointers to requirements that you can attach to code. Now, once again, the basic C language here doesn't know anything about the fact that you can attach these requirements traces. This is something that is completely orthogonal and once again a benefit of projectional editing. We've got another example for that. Let me see where it is. Just closing all the other stuff. Of course, always in the last window. So here you can see another piece of C code with a bunch of presence conditions attached. A presence condition is basically some kind of an if-def. You say that this blue stuff here should only be in the program if the configuration feature logging is selected. So we have some simple notation for a feature model which has a root feature and then 2 optional features, logging and test. And here is a configuration called debug, which has logging and test enabled, and a configuration model production, which does not have these things. Now, basically what these attachments here, annotations here mean is that the respective code to which it is attached should only be in the program if the feature is selected. Now, we're looking at this in product line mode. We can also look at this thing in variant mode, and now we have the debug configuration where you can see that the report statements are in the program, including the list. And if we switch this to the production configuration, the thing goes away. Of course, this is still editable. So because of projectional editing, you can basically put a bunch of if statements into your projection rules and show programs in different variants, which is very important for us in this product line context. Now, I've shown you all these interesting features about MPS's editor, and in fact I think the editor and the projectional editing is the main reason why people would use MPS. But it's also a very nice integrated environment for all kinds of languages, for example, or I should say for all kinds of language aspects. You can define the language structure, you can define editors, you can define constraints that restrict where certain program elements can be used. You can have type system rules. Type systems are very sophisticated. There is a inference engine running which also supports type inference, but very nice. There is, we don't do that here, but there is support for refactorings, for data flow analysis, and of course there is support for transformations in a very convenient way, because if you, for example, go back to our decision table here, just go to this, nope, here, component with decision table, that guy, that is transformed into basically a bunch of if statements, as I said. So let's show this. Let's go to build and say save transient models and rebuild this model. So this now generates the executable C code we can run on our target environment. And it has also protocolized or logged all the changes. And if we go here, you will probably see that it's still a decision table. If we go further in the transformation chain, you just never really know when it starts changing stuff. Now this has changed. Now this is not a decision table anymore. It is now has been transformed into other things. Here is the decision table. It has been transformed into nested G switch statements. So there has been a transformation from decision tables to this G switch. And then if we continue, these G switch guys, yeah, now they are basically transformed into a so-called block expression, which is a kind of, if you will, an inline function kind of, and that will be reduced further to, well, as I said, you never really know when it happens. This has been transformed into function calls to these generated functions with if statements. So my point is that you can easily have several language extensions, each of them with type systems, independently developed, use them together in programs, and also have multiple levels of transformation where you have, like, decision table to G switch to block expression to C function calls. And so this whole environment of working with many modularized languages is extremely powerful, and at least I haven't seen this in any other tool. So that's a short reason why one would want to use MPS, and well, I hope it convinced you. It is a little bit of effort to learn, but any powerful tool is. It's certainly worth it. Thanks for watching.